So today I was going to talk about some applications. So application to differential equations is really just kind of like a nicer way of saying word problems. Right, like yes, it's meant to model some real world kind of situation or thing, but when it all boils down to the nitty gritty, it means you're going to be doing a word problem. It means someone's going to give you some information, we're going to interpret it, and then try to figure out how to solve that kind of thing. So let's, okay, no, don't do that. Okay. Let's look at some examples. They can be a little bit lengthy, but it's fine. So let's start with the following. Assume the outside air temperature. So you might not want to write down the entire thing. You might just want to write down the pertinent information. I'm going to write down the problem. You can write down whatever you want. The outside air temperature is, is capital T at Lake Tahoe is a function of time, which we'll write in lowercase as lowercase t, and that the rate of change of temperature is directly proportional. Don't really need the word directly there. It's not giving you anything more. I suppose it's in contrast to saying like inversely proportional. That's something else we could say. Directly proportional just means proportional to the time t. Additionally, if time equals 1 hour, then the temperature is going to be 25 degrees Fahrenheit. And at a later time of 3 hours, the temperature is going to be 41 degrees Fahrenheit. We're going to break this out into a few different things, but basically the real kind of end question, the question we want to answer is, what is the temperature at time equal to 4 hours? Now, there's a lot of buildup in between here and there, but that's kind of the gist. Let me ask you all a question. If temperature is directly proportional to time, and we know that the temperature at time 1 is 25, the temperature at time 3 is 41, do we expect the temperature at time 4 to be more than 41 or less than 41? More, right? Because I think, right, I can see that the temperature is increasing as time goes on. There's nothing in the words here that are telling me that's going to like change direction in some way. If temperature is directly proportional to time and they're both growing, then they're both growing. So before we can do any of this, we need to first write a differential equation for the system. Okay, so let's see. We've been told that temperature is directly proportional to time. That's pretty straight, or sorry, apologies. Not temperature is directly proportional, that the rate of change of temperature is directly proportional to the time. So when I see that, I'm thinking, okay, well, that means the rate of change of temperature, dt, has to be a multiple of time. So K times T. You can use whatever constant you like. K is pretty standard though. That's it. That's the answer to part 1. We wrote a differential equation for temperature in terms of time. Or more generally, describing the system. Thing two, question 2, solve it. So when someone says to solve a differential equation, what they mean is find the function. So we are looking for temperature as a function of time, right? If we have the derivative of temperature with respect to time, that means we're looking for this top thing as a function of this bottom thing. Looking for. Okay, great. So if I can, well, really, I only have two options, right? I can either separate variables, or if I can't separate, then it's the first order linear integrating factor deal, which I mean, that's also fine, but I would definitely prefer to separate variables if I can. And we totally can here. I'm just going to bring the little dt over to the right. So I'm going to rewrite this as dt equal to kt times little dt. All I did was essentially multiply both sides by little dt. Totally fine, right? There's nothing wrong with that. And then I'm just going to integrate both sides. So the integral of dt is equal to the integral of k times t times dt. Stop me if you have questions. I'm happy to explain something more if I've done a poor job of, or even if I've not done a poor job. If I just said words too fast, let me know. Okay, so now we are going to integrate. The integral of dt is just t. If you prefer, you can write a little 1 there. The integral of 1 is t. You don't need the 1 though. And then on the other side, you're going to get k times t squared over 2 plus another constant c. We definitely want to use different constant names for different constants. All right, there's our general solution. Yeah. And I guess, go ahead.
Is k just a constant?
K is just a constant. And the reason we knew there was a constant there was because up here we said that the rate of change, so I will point out, right, this is the rate of change of temperature. It is directly proportional to. When something's proportional to something else, one's a constant multiple of the other. So this is proportional to, and then of course time. So that's, but you can use K or C or whatever. Just make sure you're consistent and don't reuse the same constant for other things. All right, and I guess since we have initial conditions, we should plug those in and solve them as well. So let's see, I believe we had at time equal to 1, we have the temperature is 25, and we have at time equal to 3, temperature is 41. There's not a lot of solving we have to do here, right? Temperature is already solved for, so we can kind of just plug these in and solve for K and C pretty readily. So I'm going to plug in 25 for temperature and get K times 1 over 2 plus C. I can't actually solve for K or C yet. That's pretty typical if I don't have the value at time equals 0. And then plugging in the other thing, I'm going to get 41 equal to K times 3 squared over 2 plus C. There's a lot of ways we could solve this. An easy way to do this, I see, is that since both of these have a C in them, just the exact amount, same amount of C, I could subtract these from each other. And I guess I'll subtract in the way they're written, even though I'm going to get negatives, that's fine. 25 minus 41 is negative 16. 1/2 minus 9/2 is negative 8/2. So I get K times negative 8/2. And C minus C is 0. Or you could have subtracted the other way, but yeah.
I feel like just like isolate C.
Totally could. I feel like it's more writing though, but you're right. You're right. We could totally say, I'm going to say here that C is equal to 25 minus 1/2 K. And here I'm going to say that C is equal to 41 minus 9/2 K, and then set those equal to each other. Like we do, so if I set 25 minus 1/2 K equal to 41 minus 9/2 K, and say I bring the 25 to the right and get 16, and add 9/2 K to the left, you get 8/2 K. It's the same as the work I've done over here. I've got 16 equal to 4K. I've got 4K equal to 16. So whichever way you want to do it's fine. One way using elimination, the other way using substitution, they're equally valid. I usually try to use the method that seems easier. Here, it seemed really easy to cancel the C's by just subtracting them from each other. Either way, we get K equal to 4, and then you can plug K equal to 4 back into either one of these to figure out what C is going to be. Plugging in here, you get C equal to 25 minus 1/2 times 4, which is going to be 25 minus 2, which is 23. Now, don't make the easy mistake here. We're not done, right? If you've got C and K, then we have to go back and write what our actual solution is. And the solution is what we were looking for, which is the temperature as a function of T. So the solution here to my differential equation is that the temperature as a function of time is K, which was 4. So 4 times T squared over 2, which I should simplify just to 2T squared, plus C, which is 23. There is my solution to the differential equation. The solution is always a function or something that you could solve for as a function. All right, now we can finally, now we've done all the work, we can finally answer the question that was actually being asked, which was, what's the temperature going to be at time equals 4? Right, that was the original question. So the temperature at time equals 4 hours. Well, now we say, oh, great. We found that the temperature as a function of T is equal to 2T squared plus 23. So then we can say, great. T at time equal to 4 is going to be 2 times 4 squared plus 23, which is 2 times 16 plus 23, which is 55 degrees. And this is a pretty, I thought this type of question is standard, but this kind of setup is pretty standard, where they give you the information, you have to write the differential equation, solve the differential equation, plug in your beginning or initial values to find out what your constants are, and then finally answer some question that was asked. That's a pretty general setup for applications of differential equations. Oh, also, sorry, I forgot about the people on the Zoom. You all are, of course, welcome to ask questions whenever you want. I should pull up the chat though. Cool. And then, of course, hiding from me. Let me give you the attendance form as well. For those of you that haven't filled out yet, attendance form when you have a chance. Someone asked me a good question via email. They're saying like they saw the video or they read something and they're like, I see that you said you didn't register for the class, like attendance is not important. I said, yes, that's true. But you also still said to fill out the attendance form. Yes, that's also true. So if you're not registered via Schedule Builder, great, totally fine. Everyone's cool. But please do fill out the attendance form, even though I know your attendance doesn't actually matter because you're not enrolled in the course. Totally fine. Yeah, let's do some more examples. Unless you have questions about this one. We can always go back to this. Yeah, this one's a pretty good one too. So let's look at another example. Example 2. Assume that the volume, we'll call it capital V, of a weather balloon is a function of pressure, we'll call it X, and that the rate of change of volume is inversely proportional to the volume V. Additionally, here are some, so that's kind of the setup. With just that setup, we could find the general solution to the, we could write and solve the differential equation, but we couldn't find the constants. Additionally, we have some initial conditions. And our initial conditions are that, where did they go? Sorry. If X is equal to 10 pounds per square inch, then volume is equal to 40 cubic inches. And if X is equal to 15 pounds per square inch, then volume is going to be 30 cubic inches. And then the end question is going to be, so eventually we want to find what the volume will be
when X, the pressure is 18 pounds per square inch. And we should expect it to be less, right? Because as the pressure is increasing, the volume should be decreasing since they're inversely related to each other. When things are inversely related, one getting bigger means the other one gets smaller and vice versa. Okay. So same sort of deal. We're gonna first write the differential equation, then we're gonna solve it. Then we're gonna, yeah. So let's see. So my differential equation, I have that the rate of change, somewhere someone has to say something about a rate of change. The rate of change of volume, that's going to be dV dt is inversely proportional to the volume. So I made kind of a, I don't want to say a rookie mistake. I just made a mistake. It's an easy one to make though, because most of the time when we think about rate of change, we think about how your volume is changing as time is increasing, or how something is changing as time is increasing. But I should have read the problem more carefully, because what this says here is that volume is a function of pressure, not time. So the rate of change of volume is inversely proportional to the volume V, but volume, how volume changes is volume is changing as pressure is changing. So what I really should have written here, not dV dt, but dV dx, how volume is changing as pressure is changing. And it's proportional to, or inversely proportional to, the volume. So it's going to be a constant times the inverse of the volume. Again, the K just for the proportionality part, and 1 over V because they're inversely related. If volume gets larger, the rate of change of volume should get smaller. And if volume gets smaller, the rate of change of volume should get larger. That's what it means to be inversely proportional or inversely related. Okay. So we've set up our differential equation. That's all there is to the setup. Usually the setup is not too terrible, with some exceptions. So then we're going to solve. So hopefully separation it is. I can bring my V's to the left. So V times dV is equal to K times dx. And then we can integrate both sides. V is equal to the integral of K dx. That doesn't seem too bad. The integral of V is V squared over 2. The integral of K is K times X plus a new constant C. So good question. Should I solve for V first, or should I start plugging in my constants first? It's not really a good answer to that question, actually. You can kind of go either way. I'm trying to do it the way that's maybe the easiest. So if I were doing it, well, I'm going to want to solve for C and K. So I feel like what I would want to do is multiply both sides by 2 first. But I don't want to take the square root. And here's why. So V squared is equal to 2 times K times X plus 2 times C. Most people, though, probably wouldn't have written that. Most people probably would just write V squared equals 2x plus, sorry, KX plus C. They would have said 2 times K is a new constant. Let's call it K1. And 2 times C is a constant. Let's call it C1. It's totally fine to do that. And this is probably the stage where I would actually find my constants, because it's pretty easy to plug in X and V and solve for K or for C. So plugging in the first values. I know I need more room. Let's give myself some more room. So plugging in the first values. I've got X equal to 10 and volume equal to 40. So I'm going to get 40 squared equal to K1 times 10 plus C1. And then plugging in X equal to 15 and V equal to 30, I'm going to get 30 squared equal to K1 times 15 plus again C1. And I think this is another example of how we could solve for C1 in both of them, but I feel like the easier thing to do is just to subtract the first equation minus the second equation. So if I subtract these, I'm going to get 40 squared minus 30 squared, which is 1600 minus 900 equal to K1 times 10 minus K1 times 15, or 10K1 minus 15K1, and C1 minus C1 cancels out. So I end up getting 700 equal to negative 5K1, or K1 equal to, dividing by 5 is never my favorite, but dividing by 10 and multiplying by 2 is really easy. 700 divided by 10 is 70, and times 2 is 140. So it's going to be a negative 140. So there's K1, and then we can go back and find C1 by plugging into either equation. I'd probably plug into the first one and say, great, then 1600 equals K1 is negative 140 times 10 plus C1. That's negative 1400 added to 1600. So C1 is equal to 3000. So then I would go back and actually write my equation. My equation was V squared equal to K1x plus C1. So I'm going to get V squared equal to negative 140x plus 3000. And now I feel like it's fine to take this. Now is a good time to take the square root and say, great. So then V volume as a function of x is the square root of negative 140x plus 3000. I don't need the plus or minus here because I know it has to be a plus because I'm talking about volume and it wouldn't make sense to have a negative volume. So there is the solution to my differential equation. Let's think about this for a second, just to make sure it makes sense. If x gets bigger, does volume get bigger or smaller? It's going to get smaller, right? Because the larger the x value, the more negative this part will be, which means it's going to decrease the overall value of this thing. So yeah, this seems sensible. As x increases, volume is going to decrease, which is exactly what it means for things to be inversely proportional. We've done all the work. Now we have to answer the question that was asked, which I know is hard. We're going to be like, oh, wait, there's still something else to do. Yeah, we go back and we're like, okay, the question was, what was the volume when x is 18 pounds per square inch? So that's not too terrible. All we have to do is go back and plug in x equal to 18. So the volume when x is 18 is going to be the square root of negative 140 times 18 plus 3000. And I probably would just leave it like that if I was doing a homework problem or taking a test. Maybe it simplifies down to something nice, but I would leave it. Okay. Questions, comments, thoughts? This is kind of the end of differential equations. I mean, we do it for like a week-ish, and then it's on to the next thing, which is going to be some 3D graphing type stuff. So that's where we're going next. Is after this is totally changing gears, doing something totally different. And then we'll do that for a little while, and something totally different, right? Again, it's kind of all the leftovers from calculus. Like, what do we need to get at the end of calculus? Here's what it is. Let's look at a couple more pretty typical examples. Yeah, we'll look at that one. How much time? Oh yeah, we got time. Yeah, so tank problems are pretty standard problems when it comes to differential equations. When I say a tank problem, what I mean is, well, something like this. A tank initially holds 100 gallons of solution with 10 pounds of salt dissolved into it. Okay. Then a mixture containing 2 pounds of salt per gallon. Seems like a pretty salty mixture there. Is added to the tank at a rate of 4 gallons per minute. The well-stirred solution, right, is drained from the tank at the same rate. At rate of 4 gallons per minute.
So we're adding 4 gallons per minute of the salty mixture, and then we're draining 4 gallons per minute of the whole entire solution.
So let's write some things down. So first and foremost, let's write and solve the differential equation. So I guess I should say, I won't focus too much on tank problems because sometimes people will totally skip them, but I feel like you should at least see one. You should all let me know if your professor talks more about tank problems on Wednesday. I also try and look at his notes, but not as easy to access his notes. And everyone's in Lee's class, right? Is anyone not in Lee? Anyone? All right, everyone's in Lee. Okay, great. I don't even know who I'll have to find who the other professor is, but as far as I know, everyone's in Lee. Okay. So I like to draw a picture here. Here's my tank. It's got 100 gallons of stuff. And it's always going to have 100 gallons, right? Because we're always putting in the same amount of volume as we're taking out. And then into it, we're putting 4 gallons per minute. And we're putting in a mixture of 2 pounds of salt per gallon. And out of it, we're taking 4 gallons per minute. So we want to write a differential equation for the system, and I should have been more specific. We want to write and solve the differential equation for the system, meaning how much salt there is at time t. So it's important to be specific about this because sometimes people ask this question and they think about like what the the proportion or ratio of salt is in the tank, and that's kind of a different thing to deal with. If we're just talking about how much salt, it's really, really easy to figure out what we've got. So our differential equation, well, we know the rate of change of salt is just going to equal the rate that the salt goes in minus the rate that the salt goes out. Well, let's say that there's a lot of having to make stuff up when you do this kind of problem. Like you're just going to pick something to be the function no one told you. So I'm going to say that capital S of t is the amount of salt at time t. The amount of salt in the tank at time t. And just because we might as well write it down, we already know that the amount of salt at time equal to 0 is 10 pounds of salt. They told us there were 10 pounds of salt in the tank. So now let's write our differential equation. It's going to be ds dt, the rate of change of salt per minute, equal to, so how much salt's going in? Well, the way I typically think about the salt that's going in is it's the, I always want to, there's always a word I miss here that I feel like it's the volume that's going in times the, there's words I can't quite find here. I don't want to use the word rate because I've already used the word rate. So the rate of salt is just the rate of volume times the, oh my gosh, I can't find the word. It's like the proportion of the volume, or there's a better word though, the concentration. Concentration of volume. So it's the rate of volume going in times the concentration of that volume. So we're putting in 4 gallons per minute, and the concentration is 2 pounds per gallon. So we're putting in 8 pounds of salt every minute. So that's going to be 4 gallons per minute times 2 pounds per gallon. And the gallons cancel, and you get 8 pounds per minute. We're adding a lot of salt. Okay, how much salt's going out? This is the part that always used to throw me off when I was a student. So the salt that's going out, it's the same sort of idea. We're pulling out 4 gallons per minute of volume. So it's the rate of volume out, which is the same typically. And then multiplied by the concentration of that volume that's going out. But the thing is, that concentration that's going out is changing, because it's whatever the concentration of the entire tank is. Because we've written some very important words up here. The well-stirred solution is drained at a rate of 4 gallons per minute, meaning we're stirring it up enough so that we can assume that the concentration is kind of uniform throughout.
What did you say for the? I can't remember what you did.
Oh, fair enough. So where is that? It says the rate of volume out and multiplied by the concentration of that volume. And yes, I agree. I wrote it terribly. Not really helping there. The rate of the volume out is also 4 gallons per minute. And the concentration of the volume out. Okay, so the concentration going in was 2 pounds of salt per each gallon of volume. The concentration going out is, well, in the tank, there are S pounds of salt per 100 gallons of volume. So it's literally going to be S divided by 100. S pounds, 100 gallons. And that is the part that always used to throw me off, is that, oh, this concentration over here is changing. In the beginning, it's going to be 10 over 100 because there's 10 pounds of salt, but it's going to change as the amount of salt either increases or decreases. So here's our differential equation. Our differential equation is ds dt equals 4 times 2 is 8 minus 4s over 100. I would simplify this a little bit. I would reduce this to s over 25. And then I'd actually get the common denominator, and 8 times 25 is 200. So I'm going to write this as ds dt equal to 200 minus s all over 25. There is our differential equation. Now, we also want to solve it. And I'm going to try to use separation of variables if I can before jumping to first order linear. It totally is first order linear. You can definitely write this as s prime or ds dt plus s times 4 over 100 or whatever 25 equal to 8. But I usually like to do separation if I can. And we can. I can divide both sides by 200 minus s and write this as 1 over 200 minus s equals 1 over 25 dt.
Why do we do that?
Why? Oh, you know what? I forgot one thing. I forgot the ds here. So the reason we're doing that is because if we have ds dt on the left, our preference would be to be able to bring all the s's to the left-hand side and all the t's to the right-hand side. But we're only really allowed to multiply or divide. So what I'm really doing here is I'm saying this ds dt is equal to 1 over 25 times 200 minus s. And the only way I can get that s over to the left is along with the 200. They can't really be broken up. So I'm really dividing both sides by 200 minus s. to get 1 over 200 minus s times ds dt equal to 1 over 25. And then I multiply both sides by dt to get this up here. I multiply this by dt, this by dt. I exactly get 1 over 200 minus s times ds equal to 1 over 25 dt. So now they're separated. I've got my s's on the left and my t's on the right. Now we're going to integrate. So we get the integral of 1 over 200 minus s ds equal to the integral of 1 over 25 dt. Okay. The integral of 1 over s is the natural log of the absolute value of s. The integral of 1 over 200 minus s is similar, but not quite the same. It's going to be the natural log of the absolute value of 200 minus s negative equal to t over 25 plus a constant. Good question. So let me ask you, what's the derivative of the natural log of x? Right. Okay, slightly tougher question. What's the derivative of the natural log of 6 minus 2x? Well, it's still 1 over 6 minus 2x. What do I have to multiply by, though? Which is? Exactly. So the reason we need this negative here is because if we take the derivative of the natural log of 200 minus s, its derivative would be 1 over 200 minus s times the derivative inside, which is -1. Since I don't have a -1 up here, I need a negative there to account for that negative. The short answer is you divide by the coefficient of your variable when you're doing this kind of reverse chain rule thing. All right, solving for the s. I'm going to multiply both sides by -1 with the natural log of the absolute value of 200 minus s equal to negative t over 25 plus a new constant, let's call it c1, and then exponentiate both sides. So you have the absolute value of 200 minus s equal to e to the negative t over 25 plus c1. And then we rewrite it as the absolute value of 200 minus s equal to e to the negative 2 over 25, sorry, t over 25, and e to the c1, and that's a new constant. People usually like to call it a. You can call it whatever you like, though. People call it C naught, people call it A, people call it whatever. So what we've really got here is our solution is, well, our next step is the absolute value of 200 minus s is equal to a e to the negative t over 25. Usually we would have dropped the absolute value way before. So I wanted to show you guys something because I think it's kind of worth seeing. The whole idea here is the why we can actually drop the absolute value. Because what you're really saying is whatever this is equal to this. So whether the insides here are negative or positive, after you make them positive, you get whatever this is. So the way we can adjust for that is just saying, well, that means the insides here are either going to be plus or minus a e to the negative t over 25. And whatever plus or minus a is, we can just say, well, great, that's our final constant. So we end up getting 200 minus s equal to c e to the negative t over 25, which solving for s gives us s equal to 200 minus c e to the negative t over 25. And there is the general solution to our differential equation. I didn't play, so I haven't found C yet, but what I did here was I said, this is going to be C. Yeah, which is not the choice I would normally make, but it's the choice that is usually made. So I just wanted you to see it that way because that's usually what someone's going to do if they're doing it this way. We could have called it anything. We could have called it A again. We could have called it C naught. In fact, let's call it C naught, just to make sure we're really differentiating here. So now all we have to do to finish solving our differential equation is use our initial condition. Our initial condition was that at time 0, we had 10 pounds of salt. So if I plug that in, that means I'm going to get 10 equal to 200 minus C naught e to the 0 over 25. The e to the 0 is just 1. So that means 10 equals 200 minus C naught, or C naught is 190. So our final actual solution is going to be S of t equal to 200 minus 190 e to the negative t over 25. Cool. We can answer some questions. Sorry, I'm just thinking about one thing for something. Oh yeah, okay, that makes sense. I was like, these numbers seem weird, but no, they're totally fine. So then you can answer all sorts of questions like, how much salt will there be after 25 minutes? And then you're just plugging in t equal to 25, which is not very exciting, right? S of 25 is 200 minus 190 e to the negative 25 over 25. And that ends up being approximately 130 pounds. Or you could ask the other type of question, which is instead of saying how much stuff is there at a certain time, you can say how long will it take until there's a certain amount of stuff. So we could ask another question like, how long until there are 180 pounds of salt in the tank? So then we would set S equal to 180, and we would solve 180 equal to 200 minus 190 e to the negative t over 25. And that requires a little bit more algebra manipulation. I would subtract 200, negative 20 equal to negative 190 e to the negative t over 25. I would divide both sides by negative 190 and get 2 over 19 equal to e to the negative t over 25. And then take the natural log. Natural log of 2/19 equals negative t over 25. So then we're going to get t equal to negative 25 times the natural log of 2 over 19. And if you plug that into a calculator, that's approximately 56 minutes. I'll point out natural log of 2/19 is a negative number, so a negative times a negative is going to be positive. I feel like that feels. There's something about that feels not quite right to me. The natural log of 2/19 is not even close to 2. Seems right though. I'm curious here.
How would 2 over 19 negative 20 over 19?
Well, it'll be negative 20 over negative 190,
Oh, yeah.
which I reduced to 2 over 19. But yeah, what's the natural log of 2/19? Good question. I feel like it's pretty small. Maybe it's not though. Maybe I'm, oh, you know what? It's not. No, it's not small. Well, it is small, but it's negatively large. It's like negative 2 point something. Okay, I'm not listening. It's totally fine. Okay, here's what I think is interesting about that. Oh, what does number 1 say? Sorry about that. How much salt? Yeah, it says how much salt. Yes, that is salt. How much salt after 25 minutes? Sorry about that. Okay. Sure. So what I think is interesting about this is that if you let this process keep running. So the question that I think is interesting, but it often is the one that comes up is what happens to the amount of salt as time goes on? In other words, so when someone says what happens is you let time go on, they're really asking you to take the limit as time goes to. So if we find the limit as time goes to infinity of our S of t, that's going to be the limit as time goes to infinity of, where is it? 200 minus 190 e to the negative t over 25. And as time goes to infinity, what happens to e to the negative infinity? I never like e to the negative infinity. I would definitely rewrite this as the limit as t goes to infinity of 200 minus 190 over e to the positive t over 25. So then I can say, oh, e to the t over 25 is going to e to the infinity, which is infinitely large. And then 190 divided by something infinitely large is infinitesimally small, getting closer and closer to 0, which means we're going to get 200 minus 0, which is 200. Which might not seem interesting yet, but give me just a second. So what we're saying here as time goes on and on and on and on and on, the amount of salt gets closer and closer and closer to 200 pounds. Okay, 200 pounds of salt in a 100-gallon tank. What's the concentration that we're getting closer and closer to? Concentration is approaching how much? Well, 200 pounds of salt divided by 100 gallons is 2. Which is exactly the concentration that we were putting into the tank. And that is a thing that is generally true. If you have this sort of situation where you're putting in something with a concentration and you're draining out something at the same rate, then the concentration of what you're adding to the tank will be what the tank gets closer and closer to as time goes on and on and on. Always true. It's kind of neat. I think it's really neat. Like it's something like, oh, that seems interesting. Why does that happen? And it does. It's not true if you're draining at a different rate. Like if you were pulling out, say, like 3 gallons per minute instead of 4 gallons per minute, it totally wouldn't work. But if you're putting in 4 gallons per minute and taking out 4 gallons per minute, the concentration of the thing you're putting in is the concentration that the tank starts to get closer and closer to as time goes on. Kind of cool. All right, I could try to cram in another problem, but they're long problems and I only have 3 minutes, so I probably shouldn't, even though I want to. Wednesday we'll probably start talking about the 3D graphing stuff, unless I definitely have more examples like this we can do on Wednesday if we want to. But you all should probably on Wednesday let me know, like, James, you'd like to do more differential equations, or James, we'd really like to start looking at the 3D stuff because we're doing it now.